came early.
All right, so exam Thursday. This is just the list of stuff that's on the exam. 6.1 to 6.7 and 7.3. No graphing calculators. More importantly, no calculators with an integral button. How's the road out there?
That's tough.
Kind of a pain, huh? So no calculator with an integral button. There's one of those calculators. It's not a TI. I think it's a Casio, or maybe it is a TI actually.
TI, but I lost mine at Casio.
Yeah, just make sure you don't have these. Just can't use the one with the integral button. No, we've got the spare calculators back there if you
Oh, Jesus.
you know need
Just in
one.
case.
So no integral button, no graphing calculator.
I don't even know how to use it.
No note cards, no phone calculators, all the regular stuff for an exam. Exam will be the whole period. You can go when you're done. I will get them graded before next Tuesday. So take them on Thursday, I'll get them back to you on Tuesday. And let's do some practice problems. So in the review section, I didn't count the number of questions I had there. There's a bunch of questions there. But I did create a video solution for all of them. So if we don't get to all of these review questions today, you're good because there's videos for all of them. So, why that's underlined. So you can look at any of the ones that we don't get to today, or if you need to rewatch whatever, you got it there. So before we get into doing these problems, reminder that homework and quizzes are due. They're set for tonight. I've had a couple of emails asking for an extension till tomorrow night. Is that okay with everybody if we have them due tomorrow night instead?
Yes.
Is that okay?
Yeah.
We'll go with it tomorrow night, Wednesday night? Yeah.
Well, I was even gonna say, like, for studying, for the day, for Thursday, I think it would be more than at least for the review part.
Yeah.
It's a review assignment.
Yep. Okay. Sounds good.
Are we able to get back into them and do more problems
So,
after?
yep. So when a homework due date is met, so if the homework due date's not met, you can always be in the assignment, of course. But once the due date is met, you go through the grade book and not through the assignment.
Okay.
So if you have a due date that's been met and you want to review it, you go into the grade book and click review, and then you can rework any of the problems you want and it doesn't change your grade.
Cool.
So it gives you sample problems that are very similar to. Does that make sense? Does everyone understand that? So once the assignment's due date is met, go in through the grade book and not through the assignment like you normally do.
Will the quizzes be due tomorrow night too?
Yeah, we'll put everything due tomorrow night at midnight just to give a little space. Does anyone have a homework or quiz question that you want to look at before we do these ones? Do you have one?
Yes, sir.
Oh, you do?
I was stuck on a surface area problem.
Okay.
I'll have to find it.
Okay, yeah, find the surface area. We've got 2 surface area ones here that we can do, and then if you find one there, we can do a third one. Anyone else have a particular one that caused you grief?
The hyperbolic ones.
Finding a derivative?
I think it's integral document.
It looks, going from here to here is a derivative because your power is going down. So do you think it was a derivative? Take a look. Yeah, take a look and find out for sure, and we'll do it. I'll start with this first one up here, and then as you guys find those ones, we'll do those too. So let's start with this one. We are given we're dealing with a situation where we have velocity along a line, so a straight line, so you're imagining a particle or a ball just sort of bouncing around back and forth on a line. And we're given the acceleration, and we are given initial velocity and initial position, and we want to find the position and velocity functions. So we start with the acceleration function, and we're going to integrate. In order to get to velocity from acceleration, v of t is going to be whatever the initial velocity is plus the change in velocity from 0 to t, and we are going to integrate what goes in there. What are we going to integrate to get to velocity? Acceleration. And so we're just going to take that acceleration function, negative 0.01, and I'm not going to use a t though, because when we're finding the velocity as a function of t, we need to have the t in that limit of integration, and we don't want to have t representing two different things. So for the dummy variable that goes in here, I'll just rewrite this as 0.01x dx. We know the x is going away. The x is just the dummy variable used for the integration purposes. So that's the velocity function. So the velocity function is going to be, let's see, 5 plus this integral. And I'm going to write this as negative 100th instead of 0.01, so negative 100th. That constant just comes to the front. We integrate the x, we get x squared over 2, and that's going to go from 0 to t. Now, the piece that we have to remember is that this 5 is not part of the antiderivative. So we are going to plug in the 0 and the t into this stuff right here, okay? Not into the 5. So we are going to have 5 plus, let's see, we plug in the t, so it's actually going to be a negative. So we're going to get negative 1 over 200 t squared. And then we have to plug in the 0 and take the difference. But plugging in the 0 is not going to give us anything, so we're done. So there is the velocity function. That is a function of t. And then to get to position from velocity, we do something very similar. We're told the initial position is 0. So initial position is 0. That's going to give us the function, s of t is whatever the initial position is. So s of t represents the future position. It's the position function as a function of time, function of t. And then it's plus the displacement. And the displacement is 0 to t. And then we integrate velocity to get to position. And so we put our velocity function in here. But the one thing that we change is the t. We change it to an x or whatever your favorite letter is, because we don't want t both in the limits of integration and down in the integrand. So there is our position function. S of 0 is 0. So this goes in as a 0. And then we integrate here. So we'll have 5x minus 1 over, let's see, that becomes x cubed over 3. So that becomes 600. And then this will go 0 to t. And once again, this is the antiderivative that we're plugging into. So we will end up with 5t minus t cubed over 600. When the 0 is plugged in, we end up with 0, so we don't have to put anything else. We are done. This is our position function. So this is telling us the position at a future time value. Any questions on it?
Could we, what do you call it? Integrate without having specified limits? Like
Yes, so you could use an indefinite integral and get a general antiderivative and then plug in the initial value to solve for the constant. So you could do that twice, absolutely. Yeah, so you could do it either way on the test, doesn't matter to me which way you do it. If one way feels better than the other. I like to do it this way because it's more scalable and it's kind of how you see things when you look in a book. You always see this type of formula here, the initial position or velocity plus the change. So yeah, but either way, if you want to do it with the limits of with an indefinite integral, you can do that too, for sure. All right, let's see. Danny, did you figure out that one?
Yeah, I did. I don't remember which one I was struggling with because it regenerated the problem, but I had y equals x cubed over 4.
Y equals x cubed over 4.
And the limits of that integral would be from 0 to 2.
0 to 2. So x's are going from 0 to 2.
Yeah.
And we want to find the surface area of that rotated around the x-axis. Okay, so this is a cubic. So let's first get a sketch of the graph. We don't have to be super precise, but let's at least get a general sense of what this graph looks like. So I know that at 0, plug in 0, we get 0. Plug in 2 and we get 8 divided by 4, which is 2. So 2 comma 2. So it's like that, and it's a cubic. We know a cubic is going to do something like that. So just a general sketch, and we're going to wrap it around the x-axis, going that way. So when we look at our region, this is coming down here at 2, there's 1, there's 0. Did it say to use disks? Or, oh no, it's surface area. I should write that here. Surface area. We're not finding volume. Volume's always easier. Surface area and arc length are the hard ones. So when this wraps around, I'm going to not write that like that. Let's just do this type of thing. So when we take one little piece of curve and we rotate it around, we get a circle. And we want to find 2 pi r. We want to find the circumference of that circle and then multiply it by ds. And that's what creates the tiny little cone base, which we call a frustum. So it's a tiny little cone base. So let's first do that piece. Let's find our circumference. So there's the radius. So the circumference is 2 pi r. And we want to rewrite the radius here with the function, so x cubed divided by 4. So we are going to end up with pi x cubed over 2. So that is the circumference at x. If you plug in x equals 0, you get a circumference of 0. If you plug in x equals 2, you get a circumference of 4 pi. All right, so there's our circumference function. And to find surface area, which they're going to use a capital S in this book for surface area, we are going to first write down our generic formula, 2 pi r ds. So there's our generic surface area formula. Circumference, and then multiply by ds, and ds is like that little slant height, which builds our frustum. So our S is going to be integral 0 to 2. And then we've got our 2 pi r thing here. We'll pull out that constant in a minute. I didn't leave enough space. There's 2 pi r. And then ds. Now, ds, let's write that over here. Remember that ds is the square root of 1 plus the derivative squared. And then we put a dx on the outside. So we need to take our function and find its derivative. Let's go ahead and do that. So there's y. Y prime is going to be 3/4 x squared. And then we're going to square it, add 1, and put it inside the square root. So I'll come over here, finish that off. So ds will be 1 plus, when we square that, I see 9/25, and squaring the x squared gives x to the 4th. So that's what's going to come in right here. And that is our setup.
Why is it 25th instead of 16th?
That's a really good question. And I don't have a good answer for it, except that it feels like Monday. Yeah, when we square a 4, we get 16. All week. Thank you for seeing that. Any other questions on that setup there? So our only choice for integration, which we see is one of the benefits to finding surface area versus arc length, is that usually this integral that you get from the ds, all by itself is usually not integrable, usually. But with the surface area, you get this extra function out in front, which hopefully will help us to integrate.
Is the limits from 0 to 2 or 1 to 2?
Oh my gosh! That is a 0, actually, okay. It just, I did write that one correctly. I just wrote it badly. But that is a 0, yes. Why is Jeff running the Zamboni right during class? Get out of here, Jeff. Go. The only technique of integration that you really have at this stage is substitution. And if you have a square root, you let u be what's in the square root. If you have an angle, you let u be what's in the angle. If you have an exponent, you let u be the exponent. So that's what we want to let u be. So let's go ahead and come over to the side, and we'll say u equals 1 plus 9 over 16 x to the 4th. Take the derivative of both sides. The 4 comes down, and we're going to have 9/4 x cubed times dx. And here, the book loves to be clever when you look at the solutions. And a lot of times what the book will try to do is match whatever's here. They'll try to manipulate this and make it look exactly like that. My advice is to do it this way. If you just pull out this constant and rewrite this so that all you have out in front is x cubed, it's a little bit easier to just solve this thing over here for x cubed dx. Instead of trying to manipulate what's in here, just come over here, solve this for x cubed dx, and then we see that, oh, there's x cubed dx, there's x cubed dx. Just replace that with 4/9 du, and the 4/9 will combine with the pi over 2, and your constant will just be correct. Trying to manipulate this and say, oh, let's make that a 4, so let's multiply this by 2 over 2. And then, oh, let's make the numerator a 9. Let's multiply again by 9 over 9. Of course you can do that. You can always multiply by 1. But it's just a little simpler if you just get rid of the constants here, you see the variable piece as x cubed dx, isolate the x cubed dx, and then substitute. Generally the safer way to go in terms of making fewer mistakes. So x cubed dx, that pink part will all become 4/9 du, so the 4/9 comes to the front. And in here we have the square root of u du. And to come up with the limits of integration for u, we come to this equation right up here. This relates x's and u's. This is how we exchange x's and get u's. If we put in an x equals 0, we're going to get u equals 1, so that's going to be down there. Take an x equals 2 and plug it up there. 2 to the 4th is 16. Those cancel, and we get a 10. So our new limits of integration will be u limits, and they look like that. We'll cancel out a common factor of 2 here, so we're going to end up with 2/9 times pi. 2/9 times pi. And then this integral, that's going to be a u to the 3/2 divided by 3/2, and that will go from 1 to 10. Any questions there?
Don't we need to change our limits of integration?
Yeah, we did. There's 0, 2 here.
Sorry.
Oh, it's okay. 0, 2 for x.
Yeah.
And then we plug those x limits of integration into this equation, and we get u limits of integration. So yeah.
If we don't want to use u limits, it's just plugging in the original equation, right?
So if we don't want to convert limits, what you can do is just put like stars here. and say, okay, I don't know the U limits and I'm not going to find them. And then once you do this integration, then you're going to take this U expression, plug it back in there, and then go 0 to 2. Yeah, so you can do either of those is totally fine. Yeah, whatever feels best. And then we're going to just substitute in our upper and lower limits. So we end up with, looks like 4 pi over 27. Upper limit gives us 10 to the 3 halves minus 1 to the 3 halves. 1 to the 3 halves is just 1. And then the simplification, which I will not take credit, I won't take points off on the test, but usually the way you're going to see this is 10 root 10 minus 1. Anytime you have a 3 halves power, you can write it that way. Get rid of that fractional exponent. All right, any questions on any step there?
This last step is where I was getting stuck with. I find this kind of daunting, the plugging in 10 to 1 plus 9 to x to the 4 over 16.
Say this right in here,
Yeah. Or you're just plugging 10 there.
that was the problem?
Yeah. Like, well, from, I guess, just evaluating the last step.
So when you're doing that, remember that this constant is just sitting in front, so that constant's out in front. And this part is what's getting plugged into, so we're always going to plug in both limits and then take the difference.
Oh, so you don't substitute it back in, the 1 plus 9x to the 4?
Nope,
Okay.
you don't have to.
Right, and if I did, I would set the limits back to normal.
Exactly. So if you did do that, so from this stage, let's come over here, so we could write this as 4 pi over 27, and instead of u to the 3 halves, you could do 1 plus 9/16, this whole thing. This would be to the 3 halves.
Oh God, no.
And then, right? And then this would be 0 to 2.
That's where I kept getting stuck. It's just kind of mess.
So you could absolutely, that's a really weird looking 3 halves. So yeah, if you plug in here, you'll get the same thing.
Okay.
We'll have the 4 pi over 27, plug in the 2, and you're going to get 16. That cancels, you'll get 10 to the 3 halves. Plug in 0, you get 1 to the 3 halves. You'll get the same thing. Yeah, so either way. Brian, did you find the one you were looking at? So let's add one more page. And what was you had a function, right?
Yeah. It was find the derivative 13x to the 5th.
13x to the 5th.
Sinh
Sinh.
x.
Just x?
Yep.
Okay. So if we want to find this derivative, so y prime equals question mark, this is a product, and you can do it in a couple of ways. You can form the product in several different ways. I think the natural way to form this product is to think of it like this. Here you could put the 13 with the sinh if you wanted, but that's how I'm going to treat it. I'm going to treat that like f times g, and then use the product rule. So the product rule says that the derivative is first function, so there's first function, multiplied by the derivative of the second function. Derivative of sinh is cosh. So first derivative second, plus the derivative of the first. So the derivative of the first, the 5 is going to drop and we're going to subtract 1, so that's 50 plus 15, 65. If I did my arithmetic right there. Multiplied by the second function. And there's not a lot of work here. There's not much more we can do. So the only thing we can do is sort of get rid of the parentheses. I was just writing the parentheses to try to keep it clear. But we don't need them. So that will be our derivative. That makes sense?
Yeah.
Why
Good.
does it change to negative minus?
Say that once again.
Why does it change to
Oh.
It doesn't.
Because it feels like Monday. Nothing seems right. Thank you.
I'm glad Tuesday gets to feel like a Monday for you.
I know. Yeah, because yesterday felt like Monday too, though.
Just a week of Mondays.
It's a week of Mondays. Oh boy. It's only going to get better. I'm glad I won't have to talk on
I was gonna
Thursday.
say, yeah, you get to chill on
I get to
Thursday.
chill on Thursday. And then I get to grade on the weekend.
Oh yeah, that's
But it's my, like, I have a high school reunion this weekend, so when am I going to squeeze in the grading? Oh man, it's going to be rough. It's
oh
going to be
no, I
rough.
guess you can't go to the reunion.
Oh, I'm going. I haven't seen these people in 40 years. Like, oh my gosh, it's going to be weird. Okay, hopefully people are wearing name tags.
You should purposefully wear the wrong name tag.
Wear the wrong name tag. I'll wear my brother's name tag. All right, so let's go ahead to the next one on our list. So this says that we've got a culture of bacteria and we know its rate of change. So you go out, somehow you're measuring the population of these cells and you can see how fast the population is changing on a daily basis. So the question is, okay, once we know that the rate is what it is, can we predict the actual population of these bacteria? So let's try to do that. So we know that the population, N of t, so that's the population at time t, that's a future time. And a few of you came in after I mentioned this. Let me just point out that for our review exercises, all of them have a video. So if we don't get to all of them today, that's okay, because I put a video solution to all of them so that you have each one of these worked out just in case. So our future population is our current population. So we just think of going out and measuring how many happen to be there on day 1, which we call time 0. And then we're going to add the rate at which we're going to add the displacement or the change in the population on the interval 0 to t. So t is going to be our future time value, 0 is our initial time value, and we integrate the derivative of the function. Oh, can't use a t though, we already used t, so we'll just use an x. Or whatever your favorite integration letter is. Doesn't matter. As long as it's not a t. You could put a capital T up here if you wanted. You could do all sorts of things to make it work. Okay, so N of 0, they tell us that we started with 200 of these cells. And then we're going to integrate from 0 to t. We know the derivative function, so we plug that derivative function into the integrand, and we have some horrible exponent, 21972. Not a t though, we're going to do an x. So we have that. We're integrating an exponential function with a linear exponent. So anytime we have a linear exponent or a linear angle, we use the reverse chain rule instead of the chain rule since we're integrating. So 200. Anytime we integrate an exponential or differentiate an exponential, the first thing is to write down the function again. So the integral is itself. And then the reverse chain rule part, divide by the derivative of the exponent. And it's linear, so the derivative of the exponent is just the coefficient, just the slope. And this will go 0 to t. We plug in our limits of integration. Once again, the 200 is not part of our antiderivative, so that's out in front, and we're treating this as our antiderivative, so that's where the t and the 0 get plugged in. If you feel more comfortable identifying that by putting big parentheses here, absolutely, do that. So let's plug in the t for x. So we're going to have plus 50 e to the blah, blah, blah times t divided by this denominator. Now we have to subtract off the antiderivative evaluated at 0. Plugging in 0, e to the 0 is 1. So then we're going to subtract off this. And that is going to be our population at time t. There's some things you can plug into your calculator. You can get that. Of course, you can do that over here too. Divide and then add it to the 200. I'm not going to write that step down here. So that is the function that measures the number of cells at a future t value. The question then says, well, what about 14 days later? What do?
Plug it in.
Plug in 14. All we have to do is plug in 14. If we want n of 14, we're just going to come through. All this is going to be the same. All we're going to do is plug in a 14 right up here. And then type all this mumbo jumbo into your calculator and get, round it to the nearest cell. And that will be, and it is a word problem. So when you type it in and you get those simplified things, this will be the number of cells in the end. Make sense? So this is that generalization when we're not talking about position, velocity, and acceleration. This is sort of for a general quantity that's changing, whether it's a population or it could be some financial thing, whatever. So that's why I usually will do it that way, because that's how you're going to see it with non-speed, non-distance, velocity, acceleration problems. Do we need to do an area between curves? Yeah. So this is a question that involves an absolute value function. So remember that an absolute value function is a piecewise defined function, and there's no antiderivative explicitly for an absolute value function. You have to break it into its pieces. If you integrate a piecewise function, you integrate it piecewise. So you have to have a different integral for each piece. So first let's get a sketch. So y equals the absolute value of x minus 12. That's just the absolute value of x, the v, shifted 12 units to the right. Because instead of an x, it's an x minus 12, which is going to shift it. Same way it would shift a parabola. So we've got this function out here, looking like that, at 12. And then we've got this line, and that's just a line through the origin. Plug in 0 and you get 0, so it's through the origin. And that line is going to be coming out and going this way. Slope is 1/2, más o menos, like that. So this area here, we're trying to find the area of that triangle. If we use a vertical integration element, we will need 2 integrals. If we use a vertical integration element, this region right here is split at that point, and the lower curves are different. Right, so for that absolute value function, you would have to get the equation of this side, the equation of this side, and do it as 2 separate integrals. If we chose to do it horizontally, we would also need to use 2 integrals. Because if you look at it horizontally, if you look at that point right there, that is also splitting. It's so that the left curve is different whether you're above that dotted line or below it. If you're below the dotted line, you have both sides of the absolute value function. But if you're above that horizontal dotted line, the purple curve is the left curve. All right? So no matter what, we would have to split this into two. It's going to be easier to split it into two going with the vertical one where it's split right at that, at the vertex right there. So we are going to leave the functions measuring vertically. We're going to do one over here, and then we'll change the color and do one over here. So those are going to be two separate regions. So let's identify the curve on the left right here, and then we're going to identify the curve on the right right there. So we look at our absolute value function, y equals, so the definition of an absolute value function is that it's itself, what's inside the absolute values, if what's inside is greater than or equal to 0, which means x is greater than or equal to 12. Right, so if x is greater than or equal to 12, you just erase the absolute value bars. But if x is not greater than or equal to 12, so if x is less than 12, you plug in like 10. 10 minus 12 is negative 2. How do you force the negative 2 to be positive 2? You multiply by negative 1. That's how you make it positive. So this is going to be negative x plus 12. You multiply the inside by negative 1. So if the inside is negative, multiply by negative 1, and it forces it to become positive. So that tells us that over here, we are dealing with the function y equals x minus 12. That's when we're to the right of 12. And over on the left of 12, that lower function is y equals negative x plus 12. And in both cases, it doesn't matter. The top curve is always y equals x halves. So now we've got all of our curves labeled. We don't know the intersection points quite yet, so let's figure those out. So let's come off to the side. So this intersection point is between blue and purple. So we're going to set blue and purple equal to each other. There's purple, there's blue. Double everything, multiply by 2 just to clear out those fractions. And we're going to end up with, if I subtract the x there and add the 24, we'll get 24 as the x value. So this point right there is 24 comma whatever. We don't even care what the y coordinate is, but that x coordinate will be a 24. And then we come over to the other side. We're going to set x divided by 2 equal to negative x plus 12. Again, let's just clear the fraction. It's easier. Of course, there's other ways to do the arithmetic. Doesn't matter. Whatever works for you. We get x equals 8. So this x coordinate right there is 8. So now we know everything we need to figure out the area. So we'll just write the setup here. The area is going to be this green area on the left there. So that integral is going to go from 8 to 12. And then that's a vertical integration element. So we have a dx. Thickness of that element is dx. And then the height of that rectangle, it's a vertical height. So we do the upper y coordinate minus the lower y coordinate. We do a change in the y values. So the upper y coordinate is x divided by 2 minus the lower y coordinate is that one. So we're going to subtract that off. So there's our first integral. That's finding the left piece of the triangle. And then we're going to add to it the right piece. So plus the integral from 12 over to 24. Vertical again. Upper curve is still x divided by 2. So that's the upper curve minus the lower curve. The lower curve is x minus 12. Yikes. There is our setup for the integration that finds the area. Questions? Is it obvious? Okay.
I guess since this is a word problem, would it be expected on the test to graph it as well, or will we be provided graphs?
Something like this you would have to graph. I won't give you the graph of something that I would consider an algebra graph. That's, so parabolas and circles you should be able to graph. Lines, of course. The basic trig functions. Not like sine of 2x, not with a modified period or amplitude, regular sine, regular cosine, regular tangent, but not anything complicated. But these ones, yeah, these ones I would expect you to be able to graph, lines.
I have a question.
Yeah.
So if we assume this is a solid going around the x-axis,
If we were going around the x-axis?
yes, I just wanted to see if we wanted to use the shell method, what would that mean? What would be our, I just need our r and our height.
So if we were going to rotate this around the x-axis and create some sort of hourglass-looking thing or some torus-looking thing, you would want to use the washer method. So the washer method, we would use the little green and the little blue segments, turquoise, whatever that color is. We would use those. So those would create little washers as you go around. And the outer radius would be the purple curve, and the inner radius would be this lower black curve. And then over here, the outer radius of the washer would be the purple curve, and then the inner radius would be that lower black curve.
Kind of the same as what we have now, right?
Yeah, the layout is exactly the same here. It's just what would change is that we would find the area of the green being rotated around, the area of the blue being rotated around, and then integrate them both.
Sorry, just a related question. Why do we need to say squared minus squared when we are finding
The washer?
inertia?
So when we look at the shape of a washer, so the shape of a washer is a circle within a circle. So when we are looking at the area of this washer, oh, whoops, I wanted you to be a circle, I just wanted to get you in the middle. That's better. So the radius of the outer circle we'll say is capital R, and the radius of the inner circle is little r. The area of the washer is the stuff that is in between the two. So if we're trying to find that area, we're going to do the green area, which is pi capital R squared, and then we're going to subtract the whole. So that's how we're going to get the area of that yellow region. We're going to take the big disk, find its area. Well, we have a hole in the middle of it, so we're going to subtract off the area of that little disk that's in the middle. And so that's why we're getting the subtraction of the radius.
And we are factoring pi.
Pi is going to factor to the front, so then we're going to have the r outer squared minus the r inner squared. That makes sense?
Yeah.
Yeah, once you see it, it's like, oh yeah. It's geometry that makes sense. So let's get to 3 dimensions. Since that was a good segue, now we're in 3 dimensions. So we have several different ways that we build our solid objects. One is to just geometrically construct them and say, this is the base of your solid object, and then I tell you what the cross sections look like. So we're sort of constructing it from a geometric point of view. There's the base. Now we're going to put rectangles across it, or now we're going to put semicircles across it, or now we're going to put triangles across it. So this is general slicing, is when you do it this geometric way. So we have a triangular base, and when we say base, remember there's 2 bases. There's the base of your solid, and then there's also the base of your cross section. So you've got to just be a little aware. It can be sometimes a little bit of a word salad when you see the word base twice. When we do our cross sections, they are always perpendicular to your base. So if this is the base of the solid, the cross sections are always perpendicular to the base. We're not coming in with oblique slices that are coming like this. We are just going always perpendicular to the base, no matter what. Perpendicular to the base. But then we also have to know, well, what about the relationship between the x-axis and the y-axis? And so that's where you hear the word, where you might hear, the word base again. So let's see. So we've got this triangle right there. And 0, 2, 2, 0, 0, 0. Cross sections are perpendicular to the base. So the base is now the board. Perpendicular to the base means the cross sections are coming straight out of the board. They are cross sections perpendicular to the base and parallel to the y-axis, and they're semicircles. So these semicircles could come out of the board like this, or they could come out like this. We have two different ways that we could be drawing semicircles. They tell us parallel to the y-axis. So our cross sections, we're going to draw a vertical element, and you can imagine this green semicircle coming out of the board. The other option is it could go this way, right? We could have semicircles that are parallel to the x-axis. We don't, so let's get rid of that. So these are parallel to the y-axis, perpendicular to the x-axis. It could have been said either way. So it could have said perpendicular to the base and perpendicular to the y or x-axis. In this case, it could have said perpendicular to the x-axis. All right, so now that semicircle, we're going to say that that vertical element is at a random x value. There's the center of our semicircle. Let's pull that semicircle out and just have it separated, just to look at it more carefully. So there's our semicircle. There's the center of it. So that thing is turned and sitting right on top, coming out of the board. And they get smaller and smaller as you go to the right, larger and larger as you go to the left. The biggest semicircle would be over here at the far left. Okay, well, when we find the area of a semicircle, the area of a semicircle is pi r squared divided by 2. So that is the area of our semicircle. Pi r squared, the area of the full circle, and then you chop it in half. Well, the radius, there is the radius right there. The radius of our semicircle is right there. Okay. We're going to use the function to generate that radius. But keep in mind that the function is going to measure the full distance from the x-axis up to that diagonal line. The radius is only half of that. Everyone see that? That the purple is half the green? So when we come up with the equation for this line, we're going to have to chop it in half. Because the radius of the semicircle is only half the distance up to that diagonal line. Well, that line is y equals negative x plus 2, y-intercept of 2, slope of negative 1. So that tells us that the radius is going to be minus x plus 2 divided by 2. That function is measuring the full distance right there, but the radius is only half of that. So when we plug that in, what do we get? We get pi over 2 multiplied by the radius, negative x plus 2, all divided by 2, quantity squared. Let's go ahead and simplify our area function a little bit before we move on. So that's going to be a 2, squaring that's going to be a 4. 4 times 2 is 8. So we'll have pi over 8 out in front. And the polynomial part will be x squared minus 4x plus 4. If it's Tuesday, if it's Monday, it might look a little different. So any questions on generating the area? So we're finding the area of that semicircle right there. And now, that's 2 dimensions. We have 2-dimensional area. To get volume, we rotate around, well, no, not rotate. We're going to add up all of these little volumes to get the total volume. So we have that cross section, which is area, and then we imagine putting a dx on it and creating a little tiny volume, so it's a slice instead of a cross section. We add up all those little volumes to get the total volume, and that is done with integration. So we're going to integrate 0 to 2. We integrate the area function to get volume. So if we integrate this area function, we will, in fact, get the volume. And not too crazy for this integral. Plugging in the 0 gives us nothing, so we really can focus on the 2. 2 is going to be 8/3 minus 8. Oh, plus 8. All right, well, that actually simplifies very nicely. So the 8 and the 8 cancel.
And the 8 and the 8 cancel.
The 8 and the 8 cancel. So we have 5/3. So that is going to be the volume, 5/3. So we've got our basic concept here that integrating area is going to give you volume. Integral of area gives volume. Okay. Let's take a look at a disk problem. This problem, we have a region, and we are not doing general slicing. So general slicing is when we describe the solid with a geometric approach. Here we do a rotation. So if you take a rotation and you go around the x-axis and your region is touching the x-axis when you're rotating, that's going to automatically create disks. So when we create our solid object through rotation, we're going to have disks, washers, or shells, as opposed to general cross sections. So here we're going around the x-axis. We're going to draw a vertical rectangle, vertical element at a random x. And we should be visualizing when that rotates around, that is creating a disk. We find the area of that disk. We know that the area of a disk is going to be pi r squared. So pi times the radius squared. That's the area of a disk. Is this going to be a dx or a dy? We see it as a dx. Because that vertical element, the thickness of a vertical element is always dx. The thickness of a horizontal element is dy. So that tells us that the r needs to be converted into x's so that we can integrate it with that dx. And that radius is the function. So we have e to the negative 2x. That is the radius. And then that's squared. So the function is the radius here. Unlike the last one where the function was 2 times the radius. All right, we simplify this. We're going to get pi. Power to power you multiply. So that tells us the area of the disk at x. If you plug in x equals 0, you will get the largest disk on the left. If you plug in x equals natural log of 4, you'll get the smallest disk on the right. So that is our area function, and to get volume, we integrate area. So we will integrate this area function to get the volume. The limits of integration are given, 0, natural log of 4. So that is the setup. Any issues? See it? We're integrating an exponential. The exponent is linear. So right up there is linear. As soon as we see a linear exponent or a linear angle or a linear quantity inside of a square root, we know we can use reverse chain rule. You could use substitution and add an extra 4 or 5 steps if you want, for sure. but we want to be efficient with our integration because it's done so commonly. Integral of an exponential is itself, just like the derivative of an exponential starts with itself, and then divide by. We look at our exponent, the derivative of the exponent is -4, so we divide by -4. And that goes from 0 to natural log of 4. So this can be done, you can treat this whole thing as your antiderivative and plug and subtract and have a pi over 4 in both pieces of it. Or you could factor that pi over 4 with the negative sign out to the front and just focus on this as your antiderivative part that you're substituting into. So we can keep that a little cleaner if we just pull that constant to the front, and then that green part, plug in the upper limit, plug in the lower limit, take the difference. So let's do it that way. So plugging in that upper limit of integration, we're going to have -4 natural log of 4. Now we're subtracting, and I factored out the negative pi over 4, so that's all the way out in front. So it's just this e thing. So it's e at the upper minus e at the lower, so then it's minus e to the 0. That gives us negative pi fourths multiplied by, what is that? I know what the second one simplifies to. How about the first one? How does that simplify to? Say that once again. Maybe.
1 over 2.
So it's going to be 4 to the -4. Everyone agree that the -4 flies up? Its superpower of being in front is that it can fly up into an exponent. So it's 4 to the -4. I think it's a little less than 1/16 though. So 4 to the -4 is going to go here. And that is going to give us negative pi divided by 4. 1 over 4 to the 4 is 1 over 256 minus 1. Is this number overall, is this a positive number or a negative number?
Negative number.
False.
Oh, never mind. Because you
Do you see it?
Yeah, I did. When you
Right?
multiply with
You
the
look
pi
here
over
and you see that leading minus, you're like, oh gosh, this is negative, it can't be a negative volume, but isn't this number negative? Because we have a tiny amount, 1 over 256 minus 1, so this is also negative. So that overall we have a positive. So we're going to write that as 256 over 256, so we get minus pi over 4 multiplied by 1 minus 256 is minus 255 over 256. So we will end up with a positive number when all is said and done, so that's great. Better be positive because it's volume. So 255 pi over 1024. Any immediate questions on that? Remember that this coefficient of a log flies up as an exponent inside. All right, let's take our 10-minute break. And if you have questions during the break, I can answer them. Yeah.
Question on this.
All right, so let's do a washer problem, or at least set it up so that we have time to get to some of the work and force problems. Okay, so we want to find the volume here. We're rotating around the x-axis. If we use a vertical integration element, we are going to end up with a washer where, let's see, we're going to have an inner radius that is from the x-axis to that curve. That's going to be the inner radius. And we're going to have an outer radius that is going to go from the x-axis all the way up to the outer curve. So that's going to be our outer radius. And that integration element we say is at a random x value down there. So that red segment rotating around creates a big disk. The green segment rotating around creates the smaller disk. And the area of the washer is going to be pi times the outer radius squared minus the inner radius squared if we factor out the pi. So, not too crazy. The functions are given to us as measuring vertical. The y is isolated, so they're already measuring in the direction that we're trying to find, the radii. So the outer radius is that red one, so that's going to be 32 multiplied by the square root of x quantity squared minus the inner radius, which is that y equals 8x. So that is our washer area at x. So let's simplify that a little bit. 32 squared.
1024.
32 squared is 1024? Really? I was not going to guess that. I'm glad you said that then. So we have that. Oh yeah, 900. Yeah, I see it. I'm seeing it. Okay, so there is our washer area at x. To get to the volume, we are going to integrate this. And they don't tell us our limits of integration, so we're going to have to do that. And we could factor out a common factor in here. So this is going to go, it looks like 0. Let's make sure though. So we're going to set our two functions equal to each other. Divide out the 8. And then what do we do? What will we divide that for? We could divide the 4. There's a more important step that you could do after you divide by the 4. You could do it now.
Square both sides.
Square both sides. If we have a square root equation, you want the square root isolated. And by isolated, we mean, with one term here, you can square here, or you could divide by the 4 first and square. Avoiding fractions will happen if we do that. And then this is, and you'll end up with the same thing. And then you subtract the 16x. This is non-linear. Anytime we have non-linear, it's usually best practice for everything to go to one side and factor. So now we know our limits of integration are
0 and 16.
0 and 16. So we're going to put a 0 and a 16. And then integrate. Pretty straightforward integral. So any issues with setting up that integral? Finding those limits of integration? All right. And again, there's a video for each of these, so if you need more detail, you can watch the video. Let's not do all of these. Let's see, let me remind myself. Let's do this one, because it's got a picture. So let's do this one. So this says we've got this is a curve you would not be expected to have to graph. This would definitely be given to you. So we've got that funky curve. We build this region, find the volume of the solid when r is rotated around the y-axis. So we're going around the y-axis. Do you see that it's best to use a vertical element? Is that obvious? That we want to use a vertical element. Because this little pinched off section down there, if you used a horizontal element, you would have to break it into two regions. Because that little pinched off piece there has a different right-hand edge down there than this would have up here. So you don't want to use a horizontal element because you'd have to use two separate integrals. But if we use a vertical element, we have the same upper curve all the way across, we have the same lower curve all the way across. So we're going to use a vertical element. And if we're going around the y-axis, what kind of shape does that create?
Shell.
Shell. Everybody agree? So if you're parallel to your axis of rotation, you create a cylinder, a cylindrical shell, if you're parallel. So we know that the area of a cylinder or a shell is 2 pi r times h. Circumference of the base, 2 pi r, multiplied by the height. All right, when we look at this picture here, we need to find the radius and we need to find the height. Well, the radius is this distance across here, and the height is the function. The height is the purple. So what is that radius?
Is it just x?
Just x. Yep. So we have a vertical integration element. Anytime we have a vertical integration element, we know we have a dx. So that means turn your general letters, r, h, turn them into x's. Well, the r turned into an x is pretty easy because r and x are the same thing. X measures the distance from the axis of rotation. So we have 2 pi r, which turns into 2 pi x. There's our circumference. And then the height part is just the function. So that's 8 divided by 1 plus 8, x to the 2. So that is the area of the cylinder at x. We can simplify that a little bit, make that 16 pi, and then I'm going to put the x on top, put the variable piece on top, so that we have that. To find volume from area, we integrate. So the volume will be the integral. They give us the limits of integration, 0 to 2. That's 16 pi. Well, I'm gonna factor only out the pi, and you're gonna tell me why I'm doing that. Any idea why I wanted to sort of keep that 16 on the inside?
Is this in log form?
Because now it's in log form. Right? Remember that log form is when the denominator's derivative is the numerator. When the denominator's derivative is the numerator, we're done. This integrates to natural log of the absolute value of the denominator. So that is log form, 0 to 2. Right? If you were to let this part be u, then its derivative is 16x dx, which is the numerator. So you have the integral of du over u. So anytime we have, and that's the relationship that's not really talked about much in Calc 1, when you're integrating 1 over x dx, well, that's working because this function in the denominator's derivative is in the numerator, and this will always turn into natural log of the absolute value of the denominator all the time. So that's what I will call log form. And of course, you could use substitution, and it'll just be a few steps, but you don't need it. So that's log form. And what I will do to indicate that this is log form, if you just do something like this, log form or something, you know, then I know that you know. Or you just say it somehow. All right, so then this is going to turn into pi on the outside. And then we're going to take the natural log part, plug in both numbers. So we're going to get ln of 33. Don't need an absolute value, that's a positive number. Minus natural log of 1. Natural log of 1 is 0. Natural log of 1 is nothing. So there's our volume. Let's do a random axis. So we have a region in quadrant 1. So we're told, at least I believe it's in quadrant 1. Let's see, let me draw it first. So x equals 1 there. Let's see, so R is the region bounded by y equals x squared. X equals 1 is a vertical line. And y equals 0, that's the x-axis. Okay, so there's our region. Our region is this shape right in here. That is the region R. And we want to rotate that around the vertical line x equals -7. So let me get a little more space up here. Let's get this axis stretched out. We're way over here at x equals -7. That is going to be our axis of rotation right there. So we're going to come around that. And they're telling us to use the shell method. So on the exam, if it says use shell method, what method should you use?
Shell method.
The shell method. So you have to use the method that it asks you to use. So shell method. Well, if we want to create shells, when you look at this region, it's both horizontally and vertically simple. You could draw a horizontal element, you could draw a vertical element, so you could do either direction. But if you're told to use shell method and your axis is over here, should you use a vertical or a horizontal element? Vertical. Good. So vertical element so that the axis and the element are parallel so that it creates a cylinder when you do that rotation. If you chose a horizontal element, what would the geometric shape end up being? A washer. Right, because there's a gap, so you would end up creating a washer. So we don't want that. And we just saw a moment ago, we know that the area of a cylinder or the area of a washer, excuse me, a shell, I'm hearing some noise, 2 pi r d, 2 pi r h, area of a cylinder. Okay. Now, this is a vertical element that has thickness dx, so we know we're integrating with respect to x. That means any of the general letters, r, h, have to be turned into x's. We can only have x's in the integral if we have a dx, until you get to Calc 3. So for us, we need to have all x's. So we want to turn that r into an x. The radius is the distance from the axis of rotation over to that. That is the radius. The height is that purple element. So what do you think the radius is in this particular case?
X plus 7.
You agree? What do you think? X minus 7?
It'd be -7.
So if we're thinking about this full distance there, we can think of it in two ways. If it's horizontal, anytime you have horizontal, you can take the right x value and then subtract the left x value. The right x value is x. The left x value is -7. So when you subtract them, you would have x minus -7, which is going to be x plus 7. And think about it this way also. If you're over here, let's just say you're at 1. 1 minus 7 would be a -6, which can't be a radius. So we need to make sure that we're ending up with a positive number if we're talking about radius. And it's very natural to want to say x minus 7 here. So you just have to think twice and make sure that it makes sense. So either do it that right minus left way, so it's x minus -7, or you can do it more geometrically and you can say, oh, this distance right here is x. That x is a positive number because our shape is over to the right. This distance right here from the y-axis over, that distance is 7. So the cumulative distance is x plus 7. So you can think of it in that geometric way or be really analytic and do x minus -7. Either way, we're going to get an x plus 7. And then the function is our height. So that's x to the 2. Yeah?
So if we were revolving around x equals 7, would it be 7 minus x?
Yes. Yep. So always right minus left. So if the axis of rotation was over here at x equals positive 7, then that distance would be positive 7 minus x. And so let's just look at that for a second. So if this is our axis of rotation at 7, this distance would be x. This full distance would be 7. The radius would be right there, which would be x, which would be 7 minus x. Yep. So it's always going to be that right minus left. Right minus left. All right, so then we can simplify this a little bit. We're going to have 2 pi multiplied by x cubed plus 7x to the 2. That's our area function. It tells us the area of the cylinder at x. And then volume, we're going to integrate the area function. Let's pull the 2 pi out in front. We'll have x to the 3, 7x squared dx. 0 to 1. Does everybody see 0 to 1? So we have to ask ourselves, what are the x values that create the cylinders that create the solid? And the x coordinates that create the cylinders that create the solid are right there. Those are the x values in there. Right, from 0 to 1. Those are the x values that create the solid object. So we're going to integrate 0 to 1. Pretty easy integral, add 1, divide, plug in 0, plug in 1, take the difference. All right. Let's do an arc length one for sure. So we'll do as many of these as we can. So curve right here, it's given to us as a function of y, and they give us y limits of integration. So when we're thinking about arc length, the key is that ds is 1 plus the derivative squared. If we're using the sideways perspective where our function is functions of y, this is going to be 1 plus x prime squared dy versus 1 plus y prime squared dx if we had functions of x instead of functions of y. So that's going to be an x prime squared. So anytime we have arc length, we've got to find our function's derivative. So let's find x prime. So x prime, we bring down the 4. The 4's cancel, we subtract 1, we get y cubed. This is going to be 1/8 y to the negative 2. So when you take its derivative, the negative 2 comes down and you get negative 1/4 y to the what?
Negative 4.
No. Negative 3. Because we're subtracting 1 from the exponent. So the common mistake is to sort of change that to a negative 1, but it should be a negative 3, right? The negative 2 comes down in front. You subtract 1 from that exponent. Negative 2 minus 1 is negative 3. So that's going to be negative 1/4 y to the negative 3. So you could write the y cubed in the denominator if you want. Doesn't matter. So we get that. So there is our x prime. Then we have to square this.
But that's a sneaky trade on that.
Say that once again.
That's a sneaky either.
Yeah, sneaky trinomial.
Yeah.
Sneaky trinomial on the way, I think. Let's see, when we square this, we don't want to do that. We're gonna just write the form and not square it out. Keep it general for a moment. Now, this is acting like A. This is acting like B. So we do a squared minus 2 times a times b plus b squared. So that's what, when we square that out, when we FOIL it or do whatever we do, that's what we get. So we did a minus b squared. That's going to be a squared minus 2ab plus b squared. And what we notice here, the sneaky trinomial thing, what we notice, it will always be the sneaky trinomial if this middle term ends up being -1/2. Because in our formula, we have to add 1. And so when we add 1, the only thing that changes when we add 1 to both sides is that that middle term turns from negative to positive 1/2. And when we look at trinomials, if the only thing that changes is the middle term, we started with a minus b, we squared it and got over to there, then we added 1, and all we did was change the middle term, sign. If you only go from negative to positive, then you still have a perfect square trinomial, and it's going to factor into a plus b squared. So this is now a plus b quantity squared. So there is what goes inside the square root. Limits of integration are given, 3 to 4. So our limits of integration are given, so 3 to 4. And we integrate the square root of this. And that's with respect to y. And so when you have this perfect square trinomial, the sneaky perfect square trinomial, this is all going to reduce really nicely. And I'll write this as a -3. It's easier to integrate now. So we have that. And when you have the sneaky square trinomial, when you go back up and look at your original function, this is a mental cue, a mental check. You look at your original function's derivative right there. Looks a lot like this. The only difference is the sign. So that tells you that you're on the right track. You still have to show all your work to get full credit, but that at least tells you, it gives you a clue that you're on the right track. Here, when we add 1, we get -2, divide by -2 is going to give us -1/8. And then this is going to go 3 to 4. All right, any part of that creates a disturbance in the force? All right, let's take a look at, let's do a surface area one. Actually, we already did do one surface area one today, so I want to make sure that we get to some of the others first. We can go back and do another one, of course, if we have time. So let's do the tank ones. So let's go for the easy one first. Oh no! Why did that not load? I think we can draw a cylindrical tank, so it's not a big deal, but I'm just curious. Sometimes the one finicky thing with OneNote is the syncing, and so I'm just going to click sync this notebook now, and hopefully it will, hopefully these things will appear. Okay, but we have a cylindrical tank, the radius is 3, so we've got this type of scenario where that's 3, and the height is 9. All right. This is the easiest one because it's symmetric in all ways. When we look at a cross section, the cross-sectional area is the same regardless of where you are in that cylinder. So we're going to draw that cross-section at a random y, and the area of that cross-section is the area of a disk right here. So that's going to be pi r squared, bless you.
Thank you.
So that's going to be 9 pi. That's the area of every single cross-section all the way through. Okay. Now, we're trying to find the work in pumping the water out the top of the tank. So first off, how far does that cross-section have to travel? How far will that cross-section that's at a height of y, if it's going to just get pumped right out the top, it's going to travel how far?
9 minus 1.
9 minus y. So that distance is 9 minus y. All right? So that gives us what we need. We're finding work. Our acronym is add volume. ADD volume. So our work, our limits of integration are the tank, so 0 to 9. Acceleration, 9.8. Density is 1,000. So that part's pretty autopilot if we're dealing with water. 9.8. And then the second D is the distance your representative cross-section has to travel to get to where it's being pumped or drained out of. So it's being pumped out the top, so its distance traveled is 9 minus y. If this tank was being emptied right at the bottom with a valve, what would that D be?
Why?
Just y. Right? If you're at a height of y and you're draining, the distance you travel is y. Right? So if you're at a height of y and you're just going out the bottom, that distance traveled is y. And with a cylindrical tank, the work done is the same whether you go out the top or the bottom. So you could actually just put a y there and you'll get the same answer. All right, then volume. And again, for the 100th time, it's not the volume of the tank. Please, no one in here write the volume of the tank for that volume. It's the volume of the slice. So you take your representative cross-section, which is area, but then you create a slice by adding a little thickness. So you have a little disc with thickness, like a hockey puck. So that's going to be the area, which is 9 pi, multiplied by dy. That is volume right there. We're talking about the volume of the slice, not volume of the tank. And so this is the easiest problem because the cross-section all has a constant area of 9 pi, and then we multiply that by dy to get the volume of the slice. And we'll go one more step here. Get the 9800 out to the front. A 9 pi can come out to the front. So those will be multiplied together. And the only stuff left in this integral is that. So whatever this simplifies to out in front, and then we're going to integrate that. We'll get 9y minus y squared over 2 from 0 to 9. Question, Sebastian?
Yeah, so for the volume, which you said it was 9 pi dy, is the reason why the volume is 9 pi is because of, I don't know, how would you say it? Because of, yeah, I actually forgot. What was it again?
Well, so it's because the area of the cross-section, when we take our cross-section, the cross-section is a circle of radius 3, and the area of a circle of radius 3 is pi r squared, so pi times 3 squared. 3 squared is 9, so 9 pi is going to be the area of every cross-section. And then if we extrude it, if we pull it a little tiny vertical distance, we add dy as the thickness to that. So that 9 pi dy is the volume of that hockey puck right there. Okay. So the thickness of this hockey puck, we call that dy. That makes sense? So is it true that it takes half as much work to pump the water out the top of the tank when the tank is half full? No way. If we're pumping out the top and the tank's only half full, that stuff at the bottom has to travel more distance than the stuff at the top, so we're not going to have just half the work. It's going to take less work to pump out the top 4.5 meters than the bottom 4.5 meters. It's going to take more work because it has to travel a further distance. So yeah, it will not be half. Won't be half. Let's look at the conical tank. This is the middle of the road tank. Not the easiest, not the hardest. When we look at this tank, when we do our cross section, we also have a disc with a radius of r. Here the radius changes though. The radius is not whatever it was in the last one, 3 all the way up and down. The radius changes depending on where your y is. So we're putting this at a random y. It depends, right? If y is closer to 0, the radius is smaller. If we're up closer to 8 meters, the radius is closer to 1. So with this one, we have got to find the equation of this line that we've got to find the equation of this line right there. The equation of that line, if we isolate x, will give us a horizontal distance from that axis through the middle of the cone. And what is the equation of that purple line? You're imagining the origin, the coordinate system you're imagining right there. It's the line through the origin. A line through the origin is just mx plus 0. And that slope is 8. Up 8 over 1. Boom. Let's go. And then if we isolate the x, now it's measuring horizontal distances. When you isolate x. So that's measuring from the y-axis over. Oh, that's the radius. Right? That is the radius of the disk at a height of y. Right? That r is x. So we know that our cross sections here are disks. So the area of that cross section right there, area of a disk, is pi times r squared. So this area is going to be pi times y over 8 squared. So this is going to be the area of the disk at a height of y. When you're at a height of 0, the area of that cross section is 0. When you're way up here at the top, the area is going to be pi over 64 when you're up there. Okay, so our acronym, work, ADD times volume. So ADD volume, well, we can kind of jump immediately to the 9800. It's always 9.8 times 1,000 for the acceleration and the water density. The second D, that's the distance traveled by your representative element. So we're trying to find that distance, which is
8 minus y.
8 minus y. Full distance minus partial distance, get the top distance. All right, so that's going to be 8 minus y. Limits of integration, the tank is from 0 to 8, so 0 to 8. Now volume. It's the volume of the slice, not the volume of the tank. So we imagine putting a little thickness in here. We create the hockey puck looking thing. So that thickness is the dy. So this volume here is the area of your cross section multiplied by dy. That is volume in green. Area of the cross-sectional disk multiplied by dy to create it into a slice, create it into a hockey puck. So we've got that. Pull out the constants. So we're going to have the 9800 in the numerator, a pi in the numerator, a 64 in the denominator, 0 to 8. Distribute, so we'll have 8y squared minus y cubed dy. And then integrate, plug in the upper limit, plug in the lower limit, take the difference.
Which one of the from W equals the integration of A dt volume, which one of them represents the gravity?
A.
A, okay.
So it's acceleration due to gravity.
Okay.
So A is acceleration, and when something is just sitting there in space, gravity is pulling on it. So that 9.8 is the acceleration due to gravity. So that is a force that's being, exerted on that cross section of water. So A is always 9.8 for us. All right, and then you integrate that, plug in your limits. The trough. So this one is the hardest one. This one, your cross sections are a little more cumbersome to deal with. When we're dealing with the trough, the important thing is the face of the trough. And we are going to need to know the width across the face of the trough. Do you see that your cross sections are rectangles? So if you look at over here, you come across the face and then you go all the way straight to the back, and then you do the other two dimensions, right? You're building rectangles, no circles. Everyone see rectangles? Right, you've got your trough and you go across the middle, you're going to have a rectangle. So the cross-sectional area, no pi, just going to be length times width. So if we call width the front, and we call that the length or the depth, whatever you want, call it the length in this case, the area is just W times L. So the hard part is finding W. L is obviously 10. So we imagine our coordinate system right there. Well, we need to find the equation of that right edge for sure. So we want the equation of this right edge. Well, let's figure out these 2 points. So it's a line, may not look like a line, but it's a line. The lower part down here, 3.5, that's 7/2 meters across the bottom. What does that make this point right here? So you divide it by 2 and get 7/4. Half of 7/2 is 7/4, divided by 2. So that's going to be those are the coordinates of that point on the right. Because 7/2, 3.5 meters is all the way across. Half of that you divide 7/2 by 2 and you get 7/4. Up here, the height of the trough is 7, so the y coordinate is 7. The x coordinate is going to be 3.5. Because it's 7 all the way across, so from the center over it will be 3.5. So 3.5, or if we write it as a fraction, 7/2. So now we have 2 points on a line. The equation of the line is going to be y minus y1 equals the slope times x minus x1. That's point slope formula. We always use this point because there's a 0 right there. And then this will be x minus 7/4 over here. The slope, we take our 2 points. It's the change in y over the change in x. So 7 minus 0 is the numerator. That's the change in y. And the x is 7/2 minus 7/4. So that's 14/4 minus 7/4, which is 7/4. So that's what's going in the bottom, 7/4. That's the change in x. 7/4 plus 7/4 is 7/2. Everyone okay with that? So this can be simplified to y equals dividing by a fraction, you multiply by the reciprocal, so we get 4 distribute the 4 because our goal is to isolate x. We want to isolate x because we're measuring sideways. Anytime we measure sideways, we need to isolate x. So x is going to be y plus 7, divide everything by 4. And what does that make w? That x is measuring that distance right there. So we just double it. If we multiply x by 2, we're going to get the whole width of the face. So x is only measuring half that width. So we're going to double it. Multiply by 2, we're going to get y over 2 plus 7 over 2 if we multiply by 2. And now we're good to go. So now we can do our setup. The work, integral of ADD volume. We are going to have the 9800, of course, comes to the front. And this trough is 7 meters in height, so 0 to 7. So we've done A and D. How far does this slice have to travel, or this cross section? What is that distance right there? Is how much? 7 minus y, because this height is at y, right? That cross section is at a height of y. W is the width across it, but its height above the ground is y. So y is this distance right here. 7 is this distance right there. So then 7 minus y is that complementary distance right there. So that's going to be our second D, 7 minus y. And then volume. Not the volume of the trough, it's the volume of a slice. So we're adding thickness to this cross section, creating a little rectangular side on the front, but then that goes all the way around, and so it creates a slab, a very thin slab. So that is the width, which we just found. So there's the width, multiplied by the length, which is 10, multiplied by the thickness, which is dy. So this part right here is volume.
Excuse me.
Yeah?
I might have missed it, but when you're calculating the width of the line, do we need to add that 3.5 that is between the two lines, basically?
So when we find, so this distance across right here is 7/2. So we're just trying to measure the distance across from there to there. So when we divide this by 2, we're going to get this distance right there. When we take the top and divide by 2, the top is 7 across. So that's how we generate these 2 points. When we create this line and solve for x, that's going to measure from the center to the right. So this measures from the center, from the axis, over to this edge. And if we double that, we'll get the distance to the other edge. Because it's shaped like that, we are going to just double. We're going to go all the way across. We're just going to double whatever the x-coordinate is. So for example, if we're down here at the bottom, y is equal to 0. X is 7/4. It's telling us it's 7/4 from here to here, so all the way across would be 7/4 times 2, which will give us 7/2.
Okay, so that point is not the origin. So the y-axis basically is -7.
No, the y-axis is right here. This is the origin.
No, where that line crosses the
Here?
y-axis. No, the one that we calculated the line equation for.
This one right here?
Yes. So it cuts the y-axis at -7, not at.
Oh, but this line crosses at -7.
Yeah.
Yes, so if you were to extend this line all the way down, it would cross in no man's land,
Okay.
right? Because we're at the base of the ground is right there. So if you did plug in 0 into this equation for x, your y value, this line extended down would be at -7.
Yeah, I think because the way it was done in one of the practices in D12 was that they calculated 2 lines, but in this method we don't need to add that because we are already.
Yes, so we've built it in that we can just double it once we measure half the distance.
Yeah, okay.
Now, sometimes in those problems, they'll use the axis at a negative y value. They'll move the axis around, but I always like to have the axis right at the ground. But you don't have to. You can make it more complicated. So let's just do one more step here, and then we'll do some hyperbolics. So the 10 can come out to the front. Do you see this? In my mind, I'm going to only pull out 5. And I want to make sure that you see why that might be beneficial. If I treat this 10 as 5 times 2, I can take the 2 and distribute it in here and make that y plus 7. And then we don't have to deal with fractions. Or you could factor out the 10 and then factor out a 1/2. It's the same thing. Either way, you want to try to get rid of the fractions if you can before you FOIL it. When you FOIL this out, when you multiply that out, it's going to be easier if there's no fractions in it. So you can either think about taking this 2 and pushing it in here, or factor out the 10 and then factor out the 1/2. Either way, you're factoring out a 5 total. And then you're just going to simplify this and integrate. So let's go one more step where we just make sure that we understand what that multiplies out to. And then the integral should be pretty easy. So this is going to be negative y squared. The cancellation of the middle terms, negative 7y, positive 7y, will leave you with just 2 terms. So you have a polynomial to integrate. Okay, let's take a look at. So let's do a force problem. This one's going to be similar, but there's no length that we have to worry about. When we're dealing with work, we're in 3 dimensions. When we're dealing with force, we're in 2 dimensions. And so here we're finding the force on this wall, the force on this dam. This will be a good practice again, because the trough tends to, the trapezoidal face tends to be the most complicated one. And we are going to have to do a W again across from here to here. That's W. And once again, think about the coordinate system as going right there. Now, once again, we are going to have to find the equation of this right edge. So we need the equation of that. Can you see what the coordinates of the lower point are? We're on the ground. So the y coordinate is 0, and the x coordinate would be 1. If we're just going, if it's 2 across the bottom, we go halfway, it's going to be 1. And then this upper point, it's 4 across the top, so this is going to be 2 comma whatever the height is, which is 3. All right. So the equation of the line, again, is y minus y1 equals slope times x minus x1. Once again, why would you not pick this point? Only if you're a contrarian would you not pick that point. It's way easier to pick 0, so y minus 0. Slope, up 3 over, how far?
2. Wait.
Over, from this point, you go up and you go over 1. So we're going up 3 over 1, so 3 over 1, and then it's x minus that x value, so x minus 1. So this turns into just y equals 3x, minus 3. And then if we isolate x, we get y plus 3, but we divide by 3. So we're going to have that. So x will be y divided by 3 plus 1. Double check. If you plug in y equals 0, you're going to get an x value of 1, which will measure the distance across there. If you plug in a y value of 3, you're going to get 2, which is going to measure the x distance across the top. So our setup then, if we're finding force and not work, so force, integral ADD, not volume, but area. And this area is not the area of the face. It's going to be the area of a sleeping rectangle. Right there. The thickness of that sleeping rectangle is dy. So the area of that thin little rectangle is w, all the way across, multiplied by dy. That gives you the area of a rectangle. So everything is going to be really parallel to the work situation. So we're going to have our 9.8. We're dealing with water behind a dam, so it's 1,000 is density. And then distance. Or depth, if you want to think of it as depth in this case, totally fine. This is a random strip at y. How deep is it? How deep? If the total depth is 3, then that slice is at 3 minus what? And total height is 3. If our representative cross section is at a height of y, then that complementary distance is 3 minus y, which is the depth. So there's your ADD. And then area, again, is area of the rectangle, that sleeping rectangle. It is not the area of the face. So it's just this distance multiplied by dy. Now, I need a little more space. Let me just move some of this over just a skosh. So this distance here, this x value, that's measuring from here over to here. That's what x is measuring. So to get w, we're going to multiply that by 2. So there's w. And then the thickness is dy. That's area. This is area. Area of the rectangle. Limits of integration. The bottom of the tank's at 0, top of the tank's at 3, so 0 to 3. And then factor the constants out, combine the variables, and integrate. Yeah?
So the reason why we multiply the 2 to the x is that x equals the length of w on that trapezoid.
2x is the length of w, right? X only measures halfway across. When you find the equation of this line and solve for x, when you have a function of y, it's always measuring from the y-axis over.
Right.
And that's not the full width of the face, right? We also have this distance over here. And because it's symmetric, we just multiply that by 2, and then we'll get the total width. So just like down here, this half width is 1, all the way across is 2. Up here, if you're right there, you're at 2. The whole top, though, is 4. You always double the x to get the full width because of the symmetry. Let's do some hyperbolics. Gotta do some hyperbolics in here. So derivatives. We need, so the hyperbolics piece of this test is very straightforward. Derivatives and integrals. Now you've got your sample tests to look at. Practice them because you don't want to lose those points. These ones are the fastest problems on the test. So when you're looking at this, the simplest thing to probably do is rewrite this in a way that has an exponent that's in the standard place. So that exponent's not touching the minus. That exponent is on sine of, or sinh of 2x. So when you find this derivative, that 4 comes down, the sinh don't change, the power gets subtracted, and you get a 3. So that's the first part. So that's the power rule part. Power comes down, base stays the same, subtract 1. But then we have the chain rule piece, which says multiply by the derivative of the base. There's the base. The derivative of that is cosh of 2x. And then we have to zip into the angle. So we start from the outside, we're moving our way in. Derivative of the angle is 2. So that's going to be, our final answer will be -8 sinh cubed of 2x cosh of 2x. So the common mistake is to forget the cosh of 2x. You have to remember that you need the differentiation of the base. Don't forget to differentiate the base. All right, here we've got a compound function. We've got 3 different functions. So we have these nested functions or a compound function. We always start on the outside. So f prime of x, log is on the outside. The derivative of log is 1 over the inside. So 1 over the inside is where we start. So we have a cosec of 11x as the inside, so 1 over that inside. And then we multiply by the derivative of the inside, and then multiply by the derivative of that's inside. So we know there's going to be an 11 here. And the easiest way to remember the signs is that the primaries are all positive derivatives, sinh, cosh, tanh. Sec, cosec, cotanh, those are all negative. So this is going to be a negative. And then we have to differentiate that cosec function. So if we want to, we go to circular functions and think derivative of cosecant is minus cosecant cotangent. This parallels that, so it's minus cosec cotanh. So minus cosec cotanh, cosec 11x, cotanh of 11x. There's a little cancellation there, so we get minus 11 cotanh 11x. So one of the coseches will cancel. Let's look at some integrals. Anyone see what the antiderivative is without even thinking? Is it in a particular form? It's in log form. If you take the derivative of that denominator, the derivative of 19 is 0. The derivative of cosh is sinh. So it's actually in log form. It's in log form right now. So this, we can write the answer down immediately. This is going to be natural log of the absolute value. And now maybe you don't need the absolute value signs here. You guys tell me, would you need those? Plus c. This is because it's in log form. Do we need those absolute value bars? So cosh is the catenary. It's the hanging cable, which sits above the x-axis. The low point on the catenary is 1. So this is always greater than or equal to 1. So you don't need them. I won't take off credit for that, but you don't need them in this particular case, because that quantity inside the log is always positive. So you don't need them. If you did U substitution, so this is a classic situation. When you're doing U substitution and your denominator is multi-termed, you typically let U be the entire denominator, take its derivative, and then you'll see that it matches the numerator. Substitution will work just fine here. All right, here we want to integrate tanh squared. Well, tanh squared doesn't have an immediate antiderivative. There's not a hyperbolic that has a derivative equal to tanh squared, just like there's not a circular function that has a derivative equal to tangent squared. We have one that's equal to secant squared and sec squared, but not this one. So here we're going to have to use this identity first. So we get that. And then we can integrate. So the integral of 1 is x, and then sec squared. So the derivative of tangent is secant squared. The derivative of tanh is sec squared. So this is going to be that. Make sense? Derivative of tanh is positive set squared, so the minus just comes along. And the last hyperbolic here, we want to integrate this definite integral of tanh, and hopefully you sort of are seeing now that tangent or cotangent, you write them as the individuals.
So on the test, are we going to have those hints for like certain identities? If they do
Great
show-
question. I can't remember. Do you read D2L regularly? I guess you will, knowing the test is Thursday. I'll put an announcement in and answer that question. I just can't remember if I put that in there or not. I'll let you know in the announcements in D2L after class. Good question. Great question. Okay, so here, in order to get to the answer, we want to think of this as sinh over cosh. And then this is in which form? Log form. So we know that this is going to be the natural log. And we just saw a minute ago, we don't need the absolute value when the denominator is always positive. So we can just write that as natural log of cosh. So if we plug in our limits of integration, we're going to have cosh of natural log of x minus natural log of cosh of 0. We have no way to simplify this first term unless we use the exponential definitions of cosh and sinh, which I said we're not going to do that in here. So we'll just simplify. That's it for the first
You
term.
mean ln of 10?
So, I put x, ln of 10. Thank you. What about cosh of 0? What's cosh of 0?
Just 1.
Cosh of 0 is 1. Hanging cable, cosh of 0 is 1. That's the only value we know on the catenary, 0, 1. And then what's natural log of 1? 0. So this is all going to simplify to that. That's how we'll simplify it. If you wanted to get fancy and use the exponential definitions, which you'll do in engineering courses down the road, you could do that here. All right, so we'll stop there. I will get the video posted after I get back to the Math Center, so it'll be up by 3. I'll double check that one slide that had an X and the video didn't seem like it was loading. I'll make sure it's loading in my office so that it's loading on your OneNotes. I'll check my email regularly for the next 48 hours, so if you have questions, email me. Yeah,
So from the previous fourth problem?
and I'll be staying here for anyone that has questions.
From the previous fourth problem, we have that,
Yes. Yes.
is it all right if we just do
100%.
that's right after, take it out?
Take that.
I think that's what I need.
Yep. Yep, absolutely. That will work. That will work just fine. Thursday.